Hello, today we study antiderivatives and definite integrals, and probably you recognize that this is the second problem, the area problem, that makes calculus and pre-calculus different. So we discussed about this problem, in very first lecture of this course, and today we will introduce antiderivatives that helps us to solve definite integral. Okay, so from the previous chapter, we study differential. So if you have some function y equal to f of x and suppose that this function is differentiable, then you may find differential of this function, right? Differential of y is dy equal to f derivative x dx. Is that correct? Or sometimes you may write dy over dx equal to f derivative, right? In this case, we say the function f of x is an antiderivative of fx. Fx is derivative of f prime, sorry, f prime x. The derivative of f is derivative of the fx, right? And f of x in that case is called an antiderivative of the derivative. Interesting, right? So in general, we have the following definition. A function f capital X is called an antiderivative of fx if f derivative x equal to fx, right? So that is almost the same with this statement. The only thing is, I replace f derivative by f and then fx by f capital. Does that make sense? So based on this definition, you will see that if a function f capital is an antiderivative of some function f, then f capital plus constant is also an antiderivative, right? In this case, I can write, in this case, fx plus c is also an antiderivative of f of x, because you differentiate this function, you get f derivative and c prime, and c is a constant, then that is just f, oh sorry, here is fx, right? F derivative of x. I would explaining here, c is a constant. Okay. So for any c, that means antiderivatives is a family of functions that is just not a function, right? If a function is antiderivative, so you just add any constant, you get another antiderivative. So that is the whole family of antiderivatives. Does that make sense? All right, so look at this. We have some family of antiderivatives, right? Look at this. What is the difference between elements in that family? For example, so you consider the function y equal to x squared. Agree? Okay, so that is your fx, right? Let's write fx equal to x squared. What is antiderivative of fx, of x squared in this case? So you may guess, an antiderivative is cubed over 3. Why? Because when you differentiate x cubed over 3, right, you get exactly x squared. Is it correct? So that is, one antiderivative, right? So from the previous observation, I will have the following: x cubed over 3 plus c is the family of antiderivatives of x squared. All right, now let's see what is the difference, right? How to graph them. Let's graph them here. So x cubed, I graph x cubed over 3 first. Here's y, here's x, right? When x equal to 0, we have 0 in here. When x equal to 1, I have 1/3. Okay, let's say 1 in here, and 1/3 is right here. Okay, so -1, I have -1/3 in here. So I have 2. I have the function is 8 over 3, right? So we might have the following picture. Okay, and here just the function is odd, right? So the graph is symmetric with respect to the origin. So I have 1 in here, -1 in here. All right, so if I add c to this graph, that means I have to move the graph up and down. Does that make sense? If c is positive, so basically we just get another function, right? By moving this graph up on the c unit. Is that correct? So basically all this have some family of of such curve. All right here. Okay, so they are just different in the constants. Let's look at this problem from another point of view. So when we are talking about antiderivative, means we are talking about how to recover a function if we know its derivative. Is that correct? For example, from here, right, from this definition, suppose that f of x. You need to find f capital, right? So that means the derivative of f capital, and you want to recover the function. What is differentiation? Differentiation means the function and you want to find the derivatives, right? And now you know the derivatives and you want to recover the function. So this is called anti-differentiation or indefinite integration. Okay, so it's what we're having here. Anti-differentiation or indefinite integration, that is recover the function if the derivative is given. Does that make sense? So we know f x, so we need to find fx, right? Or we're writing here f derivative, we need to recover the function. That is interesting, right? That is interesting problem, and you might think about that, like, yeah, this operation is opposite to differentiation, so we have anti-differentiation. So if f capital is an antiderivative of the function f of x, we can write integral of f of x dx is equal to f of x plus c, where c is constant of integration. Okay, and this is the symbol of integral. This is an integrand function. All right, so and dx is differential of x. Okay, so that's how we introduce indefinite integral. Okay, this is called indefinite integral. Now let's consider the following example. You have derivative equal to 3x. Let's find x. Find y, right? Let's find y. So by this formula of antiderivative in here, I can write the y is equal to antiderivative of 3x dx, right? That means we have to find y such that the derivative of y is 3x. So, right now we don't have any integration rule, right? We may guess that because, we have power functions and this is pretty easy to guess. So from here you might think, yeah, let's pick one y such that, you have 3 in here, right? And here you have x squared, because the derivative of x squared is x, 2x. So you have 2x, that means I have to divide by 2. So that is one antiderivative. And then I add c to this, I will get general formula of the antiderivatives. So based on this observation, I have, integral of 3x plus 3x dx is equal to 3x squared over 2 plus c. Agree? All right, let's consider another example. So I have y prime equal to x squared plus 1. Since differentiation is linear, that means, derivative of f plus derivative of g is derivative of f plus g derivative, right? Is additive, sorry. So we have, the integration is also additive. That means you might integrate each function in here. Okay, so I might think about, yeah, let's find antiderivative of x squared and 1. We just found antiderivative of x squared right in here. You see? Right here. So I can write antiderivative of x squared is, I can write like this. Antiderivative of x squared plus 1 dx is antiderivative of x squared dx and antiderivative of 1 dx, right? And antiderivative of x squared is x squared plus 2. Is that correct? We just found that in here. So what is antiderivative of 1? Antiderivative of 1 is just x, because x derivative is 1. So, you add them and then you add one more c, you get antiderivative of the whole function in here. Does that make sense? All right, so look at this, right? It's pretty easy if we work with, power functions. And of course, we need to use additivities, right, of anti-differentiation and differentiation. Okay? So if you look at this problem from another point of view again, right? So you have, y prime equal to some function f of x. And you need to find y. Such equation is called differential equations. Okay? This is differential equations. Because this equation involves differential and derivatives. How to see differential in this case? You can write, yeah, that is nothing but, dy equal to f of x dx, right? So you have differential of y, and if you write in this form, so that involves derivatives. And that is the simplest form of differential equations. I will tell you this. So finding antiderivative means solving the corresponding differential equation. Okay. Now let's talk about some properties of antiderivative and some well-known formulas, right? And you see right now differentiation doing works, even we do anti-differentiation. Okay, properties. As we have seen, antiderivative of c dx is just cx plus another constant, let's say c1, right? And this comes from, derivative of x plus c1 is just equal to c. Okay, and we have another one, antiderivative of k f of x dx, that is just equal to k antiderivative of fx dx. Does that make sense? Because that is anti-differentiation, right? And when we study differentiation, constants can be taken out from the operation. So we can do that for antiderivative or for indefinite integrals. Next one, you have definite integrals of fx plus gx or minus is just equal to f of x dx plus or minus integral of gx dx. So we just mentioned that it's because of additivities of differentiation. Okay, and you have power rule for integrals. X to the n dx equal to x to the n plus 1 divided by n plus 1 plus c, in case when n is not negative 1, right? This because we have power rule for power function. Derivative of x n plus 1 over n plus 1 is equal to n plus 1 divided by n plus 1 times x to the n. You see? And that is nothing but, x to the n. That's why this function is antiderivative of x to the n. That's what we're seeing here. And plus c. That is one of the most important rules in integration. And if you talk about trig functions, so you might have the following one. Antiderivative of psi of x is negative cosine of x plus c. Why? Because derivative of cosine x is negative psi. So if you bring negative psi, right, into another psi, you have negative cosine derivative is psi. So that means antiderivative of psi is negative cosine. How about antiderivative of cosine? So see, that is just psi of x, right, plus c, without the negative, because derivative of psi is cosine. You see that? That is the big difference, right, between antiderivative of psi and cosine. Right here. And here just plus. So you may think about tangent. What is antiderivative of tangent? So that is secant squared x plus c. Oh no, sorry. I have to write another one, right? Antiderivative of secant square of x dx is tangent of x plus c, because derivative of tangent is secant square x. And similarly, you may find cosecant square x dx antiderivative is negative cotangent of x plus c, because derivative of cotangent x equal to negative cosecant square x, right? You see, it's something like interesting, right? When you differentiate cosine, you get negative psi, and you differentiate cotangent, you get negative cosecant, and the negative will be, but when you integrate, so antiderivative of psi is negative cosine. You see that? And the last one, you might have the following formulas. I can write integral of secant of x times tangent x dx is secant x plus c, because derivative of secant is secant x times tangent x. And the last one is cosecant x times cotangent x. Integral is negative cosecant x plus c, because derivative of cosecant x, right, equal to negative cosecant x times cotangent of x. So see, right now we are doing anti-differentiation, means indefinite integration, but again, in order to solve that fast, we need to remember basic rules of differentiation. Does that make sense? That is very important. So that's why when we do differentiation, I tell you several times, please practice that as much as possible. Okay. So now let's apply these rules to find antiderivative of the following functions. First one, dx over x cubed. So for such function, I can rewrite as power function x to negative 3 dx, right? And we apply the power rule. The power rule says, we just increase the power by 1, right? And divide by that power. So I can write like this. That is x to negative 3 plus 1 over negative 3 plus 1 plus c. Don't forget that when you differentiate, you decrease the power on one unit, right? And you take the power down. But in this case, you divide by that number, right? But you have to increase the power by 1. So basically that is x to negative 2 over negative 2 plus c. That is negative 1 over 2x squared plus c. The only way to learn this topic well is just practice a lot. Now let's consider another power function, square root of x. So you write square root x power 1/2, right? And you use the power rule, you have x to 1/2 plus 1. And here you have 1/2 plus 1 plus c. 1/2 plus 1 is 3/2 divided by 3/2 plus c. Or you can write that is 2/3 x to 3/2 plus c. Okay. Another example, 2 sine x dx. So since you have 2, that is just a constant, you can take that out of the integral. You have 2 times integral sine x dx. And as we have seen here, antiderivative of sine is negative cosine plus c. So I can write that is 2 negative cosine x plus c, or that is negative 2 cosine x plus 2c. Okay, you see that is not that bad, right? It's just anti-differentiation. So what is this? Dx. In this case, you don't see any function, but your integrand function is just 1. Don't forget that it's just 1 right here, right? So this is equal to cx. C in this case is 1, sorry, so I write 1, right? According to the formula right here. According to this formula. So I just write 1x x plus constant. So that is just x plus c. Okay. Now let's apply the power rule for the following function. You have 3x to the 4 minus 5x squared plus x dx. And we have seen that integration is additive, so you made just break this integral into 3 integrals. So I write 3x to the 4 dx minus 5 integral of x squared dx, and then plus x dx. I already took coefficients out, okay, because we know that already. So you have 3 in here. We use the power rule for x to the 4th. I have x to the 5th, right, over 5, and then minus 5. I have x cubed over 3. I increase the power by 1, right, and then divide by 3. You see, these two numbers are always the same. They should be the same all the time, right? And then from here I get, x squared over 2 plus constant. If you want, you can simplify this, but that is not a big deal. Okay. Now let's consider this integral x plus 1 divided by square root of x. So we know how to integrate power functions like this, but this is fractional function, also rational function, right? Some polynomial divided by another polynomial. So how to do with this? We don't have any quotient rule, like that is wrong approach when you just separate x plus 1 on the top dx and then divide by integral of square root of x dx. We know how to evaluate each one, right? But that is wrong. Okay, that is wrong approach. So don't do this. Okay, don't do this. In this situation, we have to break the function into two functions. Look at this. So here's the general, right? If you have a plus b over c, that is a over c plus b over c. Does that make sense? So your integral equals to x over square root of x dx plus dx over square root of x. Is that correct? Because one is right here. One is right here already. You see? But when we have integral, we don't write 1 as a coefficient. So I will simplify the first integral, because x to the 1, right, divided by x to 1/2. So that is just x to 1 minus 1/2 dx plus I write x2 to 1/2. So if you still remember how we do that, with differentiation, right? Usually we try to write radical functions in the form of power functions, and then we use the power rule. We do almost the same thing for integration. Okay, so in this case I have x to 1/2 dx, and in another side I have x to negative 1/2. I just flip that. Now I use the power rule for each function. I have x to 1/2 plus 1 over 1/2 plus 1. Another one is x to negative 1/2 plus 1 divided by 1/2 plus 1, and then plus constant. So we simplify that, we get x to 3/2, and here 3/2 plus x to 1/2 divided by 1/2 plus c, and that is 2/3 x 3/2 plus 2 times x 1/2 plus constant. So that is the antiderivative of the original function. You see, in this case we need to break the function into two functions. Let's do one more example, but just very slight modification. Okay, so you have x cubed plus 3 over x squared dx. Again, you can write, I'm sorry, I think we have to change a little bit. Let me erase this, right? I write x to the 4th. Okay, so I have x, oh no, that is okay, sorry. I have x squared dx, because you break x cubed, right, over x squared dx plus 3 dx over x squared. So basically you have integral of x squared dx plus 3 x to negative 2 dx. Then antiderivative of x squared is x cubed over 3. I write in short, like just x2 plus 1, right? And then plus 3, you have x to negative 2 plus 1 over negative 2 plus 1 plus c. So you have x cubed over 3 plus 3 x to negative 1 divided by negative 1 plus c, or x cubed over 3 minus 3 over x plus c. You see, it is pretty, I would say, not difficult. Of course, maybe that is not easy at the first time, but when you practice a little bit, everything will be easy. All right, let's do one more example, and then I think we can finish this video. Let's find antiderivative of the function square root of x cube root of x plus 1 dx. So now you have product, right? In the previous example, you have quotient, and you break that into two functions because we don't know the quotient rule, and we don't have any quotient rule for integrals. Don't forget that. And of course, we also don't have any product rule for integrals. Okay, sometimes you see very difficult functions, and you see product. Please don't break this as integral of square root of x dx plus integral of cube root of x plus 1 dx. So this is wrong. Okay, we don't have any product rule, quotient rule for integrals. So in this situation, we need to find this out. So this is equal to square root of x times cube root of x dx plus square root of x dx. Now we have to convert everything into power functions, right? So I have x to 1/2 times x to 1/3 dx plus x to 1/2 dx, right? And this function is nothing but 1/2 plus 1/3 dx. And I think I can take integral of this function right away. I have x to 1/2 plus 1 divided by 1/2 plus 1 plus constant. So let's say 1/2 plus 1/3 is 5/6, right? So you have x to 5/6 dx plus x to 3/2 divided by 3/2 plus constant, and you use the power rule, you get x to 5/6 plus 1 divided by 5/6 plus 1 plus 2/3 x to 3/2 plus c. And again, you need to simplify this number and this number, and you get what you need. Let's do that. So I will do that in here. 5/6 plus 1 is 11/6. And then I divide by 11/6. That means I multiply by 6/11. Okay, let's write that right away. 6/11 times x to 11/6. Okay, plus 2/3 x 3/2, and then plus constant. And that is the final answer. So I think the most important thing in this video is we understand what antiderivative is, right? And if a function is antiderivative of some other function, so you just add the constant to that function, you get a family of antiderivatives. Does that make sense? And integration means we need to recover the function knowing x derivative. Don't forget that. Or we need to solve the differential equation. So in the next video, we will solve a couple of problems on differential equation and how to use antiderivative to solve such equation. Okay, see you.